So let's talk about on symmetries of sections of convex bodies.
Yes. So may I start, please?
Yes, you're welcome.
Okay. Thank you. So first of all, I would like to thank the organizers for the invitation, especially Sasha Stokolas, for letting me know about this conference. So I will speak about symmetries. So let me write down the title again on symmetries of sections of convex bodies. Convex bodies. Okay, so let me start with a simple question, and then we'll make it slightly more difficult. So, question we are going to speak about. Let K be a convex body in R3. So let K be a convex body in R3. Yes, let's assume that this is origin symmetric. Origin symmetric for simplicity. So I mean K is equal to minus K. Yes. And so K is something like this. This is our K. Yes. And let me write psi as the direction on the unit sphere. This is the unit sphere. Okay, and this is just a direction. I'll also write psi perp. This is the plane orthogonal to psi, so this is the set of all p's in R3 such that p dot psi is 0. This is the scalar product, okay, the inner product. Okay, so I mean here p1 psi 1 plus p2 psi 2, let me recall, plus p3 psi 3. Is equal to 0. Okay, so I have the origin, I have my direction psi, and I have the plane orthogonal to psi. And I have a section of my body with this plane. So we pick psi and consider the section. The intersection psi perp. And we are given the following properties. So this section has a symmetry of a square. Okay, so assume that this section has a symmetry of a square. What does it mean? It means that there exists a rotation by the angle pi over 2. Let me write it like this, SO2 psi perp. By this, I mean that I'm located in this subspace psi perp in the plane, and I rotate my section by pi over 2 angle here, yes, in the plane. Oh, excuse me, please, here. Let me close the window just a second. Okay, I apologize. Okay, so there exists a rotation phi.
Sorry. May I ask you a question?
Yes,
so, since your body is symmetric with respect to the origin, then the section will also be symmetric with respect to rotation origin, by yes. Pi. And you are asking if it is also symmetric with respect to pi. So you take pi a square.
Over 2, yes, yes. Okay, so phi pi over 2 of K intersection psi perp is again K intersection psi perp. So, for example, you could have something like, I don't know, a disk, yes, or you could have a square, yes. Those are figures. There are many of those, yes, that have this property. I could change the shape a little bit, yes, and you see. Okay, so we have this property. Now we assume that for any psi, for any direction, there exists this section. There is this orthogonal transformation, the rotation by pi over 2 in psi perp such that the above property is true. Phi psi pi over 2 K intersection psi perp is equal to K intersection psi perp. The question is, does it follow that K is the Euclidean wall? Okay. So The answer is yes. This is not difficult in R3. In a moment, I'll give you the proof. Yes. But the main point of my talk is to show that this is also true in higher dimensions and to relate this type of questions to other questions that are open. Okay, so how you prove this in R3? Let me go slightly quicker. I hope that my question is clear. Is the question clear? Yes. So again, what I am doing, I have my body, I have my directional psi, I have my plane, I intersect, I have a section. I know if I take this section and if I rotate it by pi over 2, it goes to itself. Then what I do next, I do another direction eta, I have another plane at the perp, I have another section. Here now I take this section and again, I rotate inside this plane, I rotate by pi over 2 my section and it goes to itself. And no matter what direction I take, all sections have this property that they have a symmetry of a square. Does it follow that the whole thing is the Euclidean ball? This is the question. So let's understand that this is sort of an exercise. But when we go to higher dimensions, this is not an exercise anymore if you formulate this question in proper terms. Okay, so let's see what we have. So let's just look at the picture. This is my body K. Yes, and I have the North Pole, for example, here. And I consider the section containing the North Pole, for example, this one. Let's think about any function you want. You have a function, any continuous function on your sphere. F is continuous function on S2. Okay, then what do you know? You assume that this function has the symmetry. Yes. So you know that if you rotate this function, restriction on this function by pi over 2, you get f itself, yes, inside the corresponding section. Okay, so the value of your function here at this point is the same as the value of your function here, because this is pi over 2. Now take a different section here, and you know that the value of your function is also the value of your function in the North Pole is equal to the value of your function here. Yes? And then you can rotate. So this means that the value of your function here, the North Pole, is the same as the value of your function on the whole equator. So this means that if this is, let's say, the point x, that f of y is equal to f of x for any y belonging to S2 intersection x perp. Let's agree that this is x perp. Okay, this is what we got. But now if you take a different point, let's say y here, yes, and we repeat the story, and we'll get that our function is also, well, y is not a good idea. Let's have that. But we also know that f of z is equal to f of w, yes, for any w belonging to S2 intersection z perp, by a similar reason. Right? And then because two equators intersect, because this green equator intersect the black one, yes, then this means that the constants must be the same, yes. From this it follows that f of y, f of x is equal to f of z, yes, since z2 intersects x perp, yes, yes, is not empty. And we are done. Because we took two arbitrary points on the sphere and the value turned out to be the same, hence the function is constant. So this is a very easy thing. Well, very easy after you think about it, yes, for a long time, yes. But now, what about higher dimensions? So what about higher dimensions? What about higher dimensions? So let's ask an analogous question. So we are given k is equal to minus k. We know that for any xi in Sn minus 1 now, let's assume n greater or equal than 3. Yes. We know that there exists a rotation. Well, let me write it like this. For any xi, k intersection xi perp has a symmetry of a cube. Yes. Does it follow that k is the Euclidean ball? What is the difference between these two questions? The difference is that now we may not apply the previous argument anymore, because if you live in this four-dimensional case, for example, take n is equal to 4, and if you take your psi somewhere, yes, this is an element of your three-dimensional sphere, and you take the subspace, this subspace psi perp is now three-dimensional. It's like R3. And then if you want to have the symmetries of the cube, so you don't know how your cube is located inside R3. In other words, you don't know where your axis of rotations are. So this is what you lost, and this is very essential. You lost your axis of rotation, so you lost variables. So you may not argue that simple anymore. This is the idea, okay? So how much time do I have? I hope 10 minutes I have here. So now let me switch to completely different questions, and I will relate this question to another one, and I will show how this question, the answer to this question, follows from another one, okay? So let's talk about completely different things. So I have a convex body. Now you don't need to assume symmetry, but if you want, you can assume that this is origin symmetric. So you have a convex body again, K. In Rn, again, n greater or equal than 2 if you want. And you do the following. You submerge it into the water. Yeah? So you submerge in a moment into the water. Okay. So by this, I mean the following. So this is your K. You have your water. Yes. And then what you do, you sort of, you chop off a fixed volume. So you chop off a fixed volume. This is what we do. So for example, fix any delta belonging to 0 volume of your K. Yes, fix any number, and you assume that this piece has volume delta of volume delta. Okay, so you are going to change the directions. You take your body, you submerge it in this direction, and you take it out, you submerge it again, and in all directions you submerge it. So let's write that this is h of psi. This is the hyperplane. What is h of psi? This is the set of all p in Rn, such that p dot psi is some t. This is the number dependent on psi. Okay, I'm just write this is the hyperplane, orthogonal to psi, yes, and having distance t from the origin. And this is the center of mass of the body. C of k is the center of mass of the body. Now, what you want to say is the following. Let me draw the picture again. This is my K. This is my water, H of psi. This is my center of mass here, C of K. The center of mass could be also underwater, depending on how much you chop off. Yes. So this is the piece under the water. This is K intersection H of psi. And you impose the following condition. You say, according to Ulam, that the body floats in equilibrium in the given direction psi. You are given the direction psi, and you say that the body floats in equilibrium in this direction if the following is true. If the center of mass of the underwater part, let me call this H minus, okay? So if this is a hyperplane H of psi, let me call this the upper part H plus of psi, the half space, and the lower half space H minus of psi. Okay, so then I have this CK intersection H minus of psi. So I have 2 points. I have 2 centers of mass. And then what you do, you connect these 2 points with the line. Okay, so if this line is orthogonal to the water surface, then we say that the body floats in equilibrium in this given orientation psi. Okay, this is the definition. Okay, so let me write this down. Yes, so K floats in equilibrium in the orientation psi if this line L, yes, connecting the centers of mass if the line, yes, L connecting the centers of mass of the body and of its underwater part, yes, is orthogonal to the water. Okay. So again, I emphasize that we chop off. So in this direction, if I have psi, yes, and I have these 2 points, yes, this is C of K again, this is CK intersection H minus of psi, I agree that we are talking about the fixed volume. So delta is fixed from this moment, yes, and forever. Okay. Then you can change. Of course, I mean, this condition is not necessarily satisfied. For example, you have the body like this. This is your center of mass, yes, and the water goes like this. This is the center of mass of the underwater part. Of course, if you look at the line passing through these points, it is not orthogonal to the water surface. Definitely the body is going to fall down. Okay, so we have this definition. And then we say also that K, I will write like this, floats in equilibrium in every orientation. Yes, floats in equilibrium in every orientation. If this condition, let me call this line Xi, this is my line Xi, yes, is orthogonal to the water for every direction Xi on the sphere. So no matter, you take the body out, you put it, yes, it floats, it doesn't kind of rotate, doesn't fall down, yes, you take it out, you rotate it in the air, put it again, the same, no matter what, how you put it, it stays. Yes. And then there is this famous question of Ulam, yes, so fix delta, yes, from 0 to the volume, well, n. Yes, if K floats in equilibrium in every orientation, does it follow that K is the Euclidean ball again? Okay. So if K is equal to minus K, if the body is origin symmetric, and delta is half of the volume, then the answer known to be yes. Okay, this was proved by Schneider. Okay, just a second, Schneider. And Falconer. And then it was proved later by Saraglu, Miroshnichenko. Sergei Miroshnichenko, who is going to speak after me. And also later it was proved also by other people, by Florentine, Jean, Elizabeth Werner, and Carsten Schutt, and others. So this is a known result. Yeah, so what I want to do, I want to reduce the previous question about symmetries of the cube of the sections to this one. Yes, let me show you. So the idea belongs to Christa Saraglu. He says just let's look at the moments of sections. So moments of inertia of sections. Okay, so let me recall what the moments of inertia are. I have only 2 minutes. Okay, let me.
Yes, few minutes.
2 minutes, yes? Yeah, okay, then I will just wave my hands, okay? So everyone is familiar with moments of inertia, so but the point is the following. So the body K floats in equilibrium in every orientation if and only if all sections, so for any psi, the sections of your body by the water surface have equal moments of inertia, Okay, let's assume for simplicity that this is minus K, have equal moments of inertia. So this means that heuristically, this is clear. This is your K, you submerge it in water. Yes, this is your section. And then, of course, if you want your body not to rotate in any direction, yes, in any orientation, then, of course, your moments of inertia with respect to any line passing through the center of mass, these moments should be the same in all directions, yes? So taking into account this condition and taking into account the previous result, we know that if the body floats in equilibrium in every orientation for origin symmetric body and for density 1/2, we know that this must be a sphere. The idea of Saroglu is to consider moments of inertia. So we have K minus K. K intersection psi perp has the symmetry of a cube, I recall, of a cube. Yes. And just to consider the moments of inertia of K intersection psi perp for any psi. One can show that if your section has the symmetry of the cube, then these moments of inertia are constant, independent of anything, of any direction. Okay? And then you can reduce one question to another and to obtain a result. So the question arises, 1 second only. Yes, the question arises what happens with other symmetries. I talked about the symmetry of the cube, but you can assume another symmetry. For example, you can assume that you have, for example, you live in R4, you have your section, this is your psi perp, that is like R3, and you have your section 3-dimensional, you have some line, some direction, and then you have a symmetry, for example, of some pentagon, you rotate about this axis 5 times and you come back. Yeah, so you have a discrete symmetry, simplest, yes, discrete symmetry of some discrete rotation about a fixed axis. So assume that for any direction, any section has this symmetry. What happens in this case? This is open. Okay, so yes. So there are many questions here. Let me please stop here. So I want to say, yes, that I wish Ukraine a victory, peace, yes, happiness and prosperity. Thank you.
Thank you. Very, very rich talk with a lot of insights. Are there curiosities or comments or questions for our speaker?
May I ask you a short question?
Mm-hmm.
Yeah, the question is, so first of all, about symmetries. So the general point of view, you need to take some class of conjugated subgroups, finite conjugated subgroups in S or M. Yes, and
yes, if you want like this, yes.
So the question can be posed something like this. And another, since since you use moments of inertia, it's like integral of something. So maybe problem can be regarded in terms of just in the prospect of Hamiltonian systems. So maybe, and you before this you were talking about symmetries of functions, and here moment of symmetry is also something integral of mass or R squared. Do you use maybe there is a general approach with Hamiltonian systems or not, or it is not?
Okay, so well, I'm not really a boy to talk about Hamiltonian systems, but there is a book by Marsden, yes, where they speak about these things in this context. I mean, this is what you're asking. But here I think it's not. It's difficult for me to say if this is related to Hamiltonian systems because. I guess not much is known here, and here moments of inertia, they appear naturally just as derivatives of centers of mass. So, of course, there is a general theory, and I recommend you to look at the book of Marsden, but I have never seen how this theory helps here for this type of questions. Everything is open here, so I don't know. But you are right, that this is in the right direction. Yes, this should be somehow used, the general theory, but nobody knows how to apply it.
Of that statement that you say that a moment of inertia is always constant, this means that if you consider a function of moment of inertia on the set of all sections, if you parameterize them maybe something like by projective space, so you get a function on a projective space, and this
yes. I see what you're saying. The point is this: what you are saying will work if your sections pass through the fixed point. Okay, but if your sections don't pass through the fixed point because you don't know, you just chop off the fixed volume, and if you're away from the center, then it's difficult to apply this. So you see,
you assume that your section are pass through the origin, not necessarily.
yes, here I used, but
Yes,
but these questions, all of these questions, they are for any density, for any delta. Yes. So if your sections pass through the fixed point, yes, then I doubt that you need these Hamiltonian systems. I think this is a completely different thing to do. But I mean, the moments of inertia you need. I mean, moments of inertia come from one side, yes, and symmetries come from another. Yes, if you want to solve the original question, then I doubt that you need all of these Hamiltonian systems. This is rather theory of manifolds.
No, okay. So
yes, yes. But if you want to
much.
speak about moments, yes, then this is my answer is I don't know. But well, probably it's true. You have to look at these Hamiltonian systems. Yes, there is the whole book of Marsden about it. Yes, but
Yes,
I don't know.
Thank you very much. Thank you very much. Very interesting things.
Yeah, thank you.
Advanced topology. So other questions?
May I ask a very general questions? Dima, just really quickly. So my understanding is that symmetric situation and non-symmetric are totally different, right? In some settings. But did somebody try to quantify how much can you perturb symmetry to keep the answer?
Yeah, good question. Yes, this is the whole. In many questions in convexity, people try to do this, but in this type of questions, I don't know. I mean, in principle, in the questions of uniqueness, at the moment you perturb, the moment you lost symmetry, you lost uniqueness. So any type of perturbation that will kick you out of symmetry will give you a counterexample rather than an affirmative answer, usually. But I mean, there is no theory here. I don't know. General answer, I don't know.
Thank you. Thank you very much. Very interesting.
Thank you.
Thank you. A very interesting talk.